Hi. Welcome to YUME project channel. It is the first time I upload a video. In this video, I will talk to you about the special probability distribution part 1. Let's go! Don't forget to subscribe and comment this video. Thank you. In the special probability distribution, I choose the distribution and in the Wikipedia on the introduction to probability and mathematical statistics. And our purpose in this chapter is to recall some special probability distribution. In many applications that recognize certain characteristics, it's possible to determine that the distribution has no special form. Typically, special distribution will depend on one or more parameters, and once the numerical value of each parameter has been ascertained, the distribution is completely determined. And special discrete distribution will be derived using the counting technique. And the discrete distribution which will be learned in this chapter is bernoulli, binomial, hypergeometric, geometric, binomial, POISSON, and the last is discrete uniform. Let's begin on Bernoulli distribution. Let's go! And before we exploring about the Bernoulli distribution, I will give you one illustration about the distribution. Consider that you play a game with your friends. You have 7 balls, which are 3 things and 4 blue balls, and you will be winner every effectively. And based on the figure, we know that there are 4 blue balls, and we will be winner if we effectively, because there are 4 blue balls and there are 7 balls, so the probability in hatches is 4, 7. And consequently, you will do it if you set the thing, and the probability of the thing is 3, 7. Let's explore about the Bernoulli distribution. On a single trial on experiment, suppose that there are only 2 events of an interest, say E and its complement EXN. For example, E and EXN could represent the occurrence of a head or a tail on a single coin toss, obtaining a defective or a good item when drawing a single item from a manufactured lot, or in general success or failure on a particular trial of an experiment. And suppose that E occurs with probability P, and consequently EXN occurs with probability Q is equal to 1 minus P. A random variable X that assumes only the value 0 or 1 is known as a Bernoulli variable, and a performance of an experiment with only 2 types of outcomes is called a Bernoulli trial. In particular, if an experiment can result only in success E or failure EXN, then the corresponding Bernoulli variable is X is equal to 1 if E element big E and 0 if E element big EXN. And its probability density function X in Bernoulli with parameter P can be expressed as Fx is equal to P power of X times 1 minus P power of 1 minus X, where X is equal to 0 and 1. And if we wanna get the expected value of X and the variance of X, we can using the definition of expectation X. So in this chapter, I get the EX is equal to P, and the variance of a random variable X is equal to P times Q. And for Bernoulli distribution, I have some examples, such as 1. We consider rolls of a 4-sided die. A bet is placed that a 1 will occur on a single roll of the die. Thus, E or the success trial is equal to 1 and EXN is equal to 2, 3, and 4 in order that P is equal to 1/4. And the other example, we consider drawing marbles at random from a collection of 10 black and 20 white marbles. In such a problem, we might regard black as success and white as failure. If obtaining a black marble is regarded as a success, then P is equal to 1/3 and Q is equal to 2/3. Next, binomial distribution. Okay, I will give you one illustration about the binomial distribution. Using the previous example in Bernoulli distribution, we consider the problem of drawing 4 balls from a collection balls where the balls are drawn one at a time and each time replaced before the next draw. We shall let x be the number of blue balls drawn and consider function 2 is equal to probability in x is equal to. And based on the figure, we obtain some permutation of 2 blues and 2 pinks. They are blue blue pink pink, blue pink blue pink, blue pink pink blue, pink blue pink blue, pink pink blue blue, pink blue blue pink. There are 6 possible permutation on the type, and each one has the same probability of occurrences, namely 4/7 power of 2 times 3/7 power of 2. Thus, the probability in x is equal to 2 is combination 4 and 2 times 4/7 power of 2 times 3/7 power of 2. So this is with sum of the probability in the 6 possible permutation. Okay, we explore the binomial distribution. Often it's possible to structure a more complicated experiment as a sequence of independent Bernoulli trials, where the quantity of interest is the number of successes on the certain number of trials. And the probability density function x in binomial with parameter n and p can be expressed as fx is equal to combination n and x times p power of x times q power of n minus x, where x is equal to 0, 1 until n. And like before, I used the definition of expected value of x to get the expectation x, so I get the ex is equal to n times p. And in the box, in the green box, I use the properties of probability density function to get the expected value of x. This is the manipulation of algebra. After I get the expected value of x or ex, the ex square case is similar with ex in the previous slide, so we obtain ex square as follows as on the slide. So after we get the ex and ex square, we substitute the value into the variance formula, so that the variance of x is equal to n times p and times q. And for example, suppose that instead of a true-false test, a 20 question multiple choice test with 4 choices, A, B, C, and D, per question is answered at random. The distribution of the number of correct answers will be the same as the distribution of occurrences of any particular one of the values A, B, C, or D. In other words, PA is equal to PB, PC, and PD, and they are 1/4. Thus, the probability of the correct answer is P is equal to 1/4 and Q is equal to 3/4. The appropriate distribution of either variable would be binomial with parameter n and p is equal to binomial 20.14. So in this case, the probability of exactly 80% correct is 0.00000036. Next is the hypergeometric distribution. In the hypergeometric distribution, I have two illustrations. The simple question, we have 10 fruits, which are 5 apples, 2 watermelons, and 3 carrots. Oh, I'm sorry, carrots is not fruit. We want to take 2 fruits without replacement. If we obtain carrots in the first drawing, the probability of obtaining exactly watermelon in the second drawing is, okay, because we want to take 2 fruits without replacement, 1 carrot drawn, so the fruits leave 9 fruits. So the probability of obtaining exactly watermelon in the second drawing is, because we have 2 watermelons and 9 fruits, so the probability that will be obtained is 2/9. And the second illustration, we found the probability of obtaining exactly 2 blue balls out of 4 selected at random without replacement from a collection of 3 pinks and 4 blue balls. We want to obtain exactly 3 blue ones x is desired. This is the example on the previous slide in the Bernoulli or binomial distribution. On the pink top, we have 7 balls. There are 4 blue balls and 3 pink balls. this population. And for example, in the blue top, we are 5 balls. There are 3 blue balls and 2 pink balls. And the probability of obtaining exactly 3 blue ones, which desired is, because we want to obtain the 3 blue ones, and in the population we have 4 blue balls. So the combination 4 and 3 times 3 and 2, 3 and 2 it is the pink balls, per over the combination 7 and 5. This is the big N and small n. So we have the probability of obtaining exactly 3 blue ones, which the set is 4 over 7. Let's explore about the hypergeometric distribution. Suppose a population or collection consists of a finite number of items, say big N, and they are big M items of type 1, and the remaining big N minus big M items are of type 2. Suppose an item are drawn at random without replacement and denote by X the number of items of type 1 that are drawn. So the discrete probability density function acts in hypergeometric distribution with parameter n, big M and big N is given by on the slide, where x is equal to 0, 1 until n. And by similar argument in the previous slide, to get the expected value of x and variance x using the definition and using the manipulation of algebra, so I get the ex is equal to big M times n over big N. Okay, for the ex square case is similar with ex in the previous slide, so we obtain ex square as follows as on the slide. And after we got the ex and ex square, we substitute the ex and ex square into the variance formula, so we get the variance x is equal to big M times n open bracket big N minus big M close bracket times open bracket big N minus n close bracket over big N square times big N minus 1. And for example, suppose that in which a bulk contains 100 microchips, 80 good and 20 defective. The number of defective in the box is unknown to a purchaser who decides to select 10 microchips at random without replacement, and to consider the microchip in the box a safe bill if the 10 items selected include no more than 3 defective. The number of defectives selected x has the hypergeometric distribution with n is equal to 10, big N is equal to 100, and big M is equal to 20. And the probability of the loss being assayable is 0.890. And I have a theorem about the hypergeometric and the binomial. For example, 10 seeds are selected from bin that contains 1000 flower seeds, of which 400 are red flower seeds and the rest are the others colors. How likely is it to obtain exactly 5 red flower seeds? Strictly speaking, this is hypergeometric, and we get the probability of this case is 0.2013. And using binomial approximation, because big N and big M is toward infinite number, then the P is equal to 0.4 and Q is equal to 0.6. So the limit big N approach infinite number from the hypergeometric distribution, we get 0.2007. It is the approach the hypergeometric distribution. So there's a closely number. Next, geometric distribution. Using the previous example, we knew the probability a certain pink ball drawn is 3-7. The probability that we will draw 3 times to get out first drawing of pink balls is, based on the figure, because the balls drawn 3 times, thus the probability that we will draw 3 times to get out first drawing of pink balls is function 3 is equal to 3 7 times 4 7th power of 2. Based on the figure, there are 5 possibles. the pink ball will be drawn on the first. To explore the geometric distribution, we again consider a sequence of independent Bernoulli trials with probability of such as p. In the case of the binomial distribution, the number of trials was fixed number n. Now, it's negative binomial distribution. In repeatedly dependent Bernoulli trials, let x denote the number of trials required to obtain R such as this. Then, the probability distribution of x is the negative binomial distribution with discrete probability density function given by fx is equal to combination x minus 1 and r minus 1 times p the power of r times q power of x minus r, where x is equal to r plus 1 until infinite number. And for the even x is equal x to occur, one must obtain the earth success on the x trial by obtaining r minus 1 successes in the first x minus 1 trials in any order, and then obtaining a success on the x trial. And for the expected value of x, this is I use the moment generating function, and we obtain the MGF of the negative binomial is on the slide. Before obtaining the expected value of x, we have to get the value of n x accent, and the expectation of x will be obtained if p is equal to 0. So we will get the ex is equal to r over p. And the variance of x, by similar argument to get the ex square, we obtain the variance of x is equal to r times q over p square. And a for example, this is team A plays team B in 7-game World Series, and the series is over when either team wins 4 games. And for each game, P when E wins is equal to 0.6, and the games are assumed independent. What is the probability that team A wins the World Series in exactly 6 games? And we have x is equal to 6, r is equal to 4, and p is equal to 0.6. So we get the probability in A wins series in 6 games is equal to 0.20736. Now, Poisson distribution. A discrete random variable x is said to have the Poisson distribution with parameter mu is greater than 0 if it has discrete probability density function x in Poisson with parameter mu of the form fx is equal to exponent minus mu times mu power of x over x factorial, where x is equal to 0, 1, 2 until infinite number. And a full expected value of x is the definition of expression of x, and I get a x is equal to mu. And by using similar argument, obtain ex square is equal to mu square plus mu. This we get a variance of x is equal to mu. And a full example, suppose that 1% of all transistors produced by a certain company are defective, and new model of computer requires 100 of these transistors, and 100 are selected at random from the company's assembly line. And the probability of obtaining a specified number of defectives, psi 3 is equal to 0.0613. And the question number 2, the number of calls that arrive at the switchboard during 1 hour in Poisson distributes, which means mu is equal to 10, and find the probability of occurrence during an hour of each of the following events when exactly 7 calls arrive, and we get the probability in x is equal to 7 is exponent minus 10 times 10 power of 7 over 7 factorial. And the second question, at most 7 calls arrive on the slide, and the between 3 and 7 calls arrive on the slide. The last discrete distribution is discrete uniform distribution. And for discrete uniform distribution, we consider you have 8 balls in the top. They're pink, yellow, orange, red, green, white, blue, and purple ball. And if you want to draw one of the ball, the probability that you draw one ball is, if you wanna take the yellow, so the probability is 1 over 8. And by similar argument of the yellow balls, for the orange, red, green, blue, white, purple, pink, you also have the probability that you draw one bolt is 1 over 8, because this is you never like the which ball where will you draw. So the probability of each of the color is the same. And the question number 2, you might assume that you're playing a game with your friend using one die. And when you throw the fire dice, the possible value which appear is 1, 2, 3 until the 6. And each time the dice is thrown, the probability of a given score is 1 over 6. And the question, how about the dice below? And the dice below, the first is have a value which appear. So the probability of the dice is 1 over 8. And for the below, this is the 1 over 20. Many problems, essential those involving classical statement of probability, can be modeled by a discrete random variable and assume all of its value with the same probability. And it's usually possible to realize such problem to set of consecutive integers 1, 2 until big N. And the discrete probability density function of x when discrete uniform with parameter big N is given by fx is equal to 1 over big N, where x is equal to 1, 2 until big N. And of course, for the value of x and the variance of x by similar argument in the previous slide, we get the ex is equal to big N plus 1 over 2, and variance of x is equal to big N square minus 1 over 12. And for example, we have considered a multiple choice test. If we associate the 4 choices with the integers 1, 2, 3, and 4, then the response x on any given question that is answered at random is 1, 4.